Good morning. Today we'll be discussing and describing in detail what we call trigonometric functions in terms of analyzing its key features either by hand or by the use of technology, in this case, Desmos or our TI-84 calculator, in terms of the what we call the amplitude, the period, and the frequency of our sinusoidal or trigonometric functions. But before we go there, let's see first one of the real life applications of our trigonometric function. As you can see right now, this is our International Space Station. We're using a tracker in here that specifies the location of our International Space Station and, in fact, what its path is relative to the Earth's surface, and we see that that is what we call a sinusoidal path in there, where you can see right now it's almost at its minimum, sorry, at its maximum value, going towards its minimum value. So again, you can check this out on our ISS tracker or International Space Station that gives us the real-time location of our International Space Station. So you can see it on satellite. We can also see it on our terrain. And as we can see on our terrain right now, at this time, our space station is actually in the United States, almost on going to the East Coast right now. Most probably, probably it will be going to um, New York, most probably in this particular time. So you can check the orbital path in here, the horizon as well, and everything else that you can see. So this is one of the applications of what we call our sinusoidal function. Let us now go and use our TI-84 calculator in trying to see an actual graph of a sine function in here. So as you may see on top, it says that this is in radians. So always in our calculator for trigonometric function, it will always be, or it should always be, in terms of what we call the radian measurement. So in order to graph it, let's go to y equals and then type in sine of x in this case. Again, always make sure that it is in radians on top in there. And then let's see how the graph of this one looks like. So there we go. That will be our sine function in there. We can actually zoom it in if we want to, just to clearly see it. So that's zoom in the number 2 and then press enter just to clearly see how the graph actually looks like. So there we go. And that is our sine function in that case. This time we're using our Desmos graphing tool in here. This is Desmos Online. So in order to put it in here, so we click on our keypad button and then put in y equals first. And then under the functions in there, we can click on sine or cosine. Let's try to see this sine function and we'll put an x in there. And as we may see from the graph, this doesn't look like our typical sine function from the TI-84 calculator a while ago. So we're going to do something about this first. In terms of going to our settings, in this case, and make sure that it should be in radians, because as you may see, the highlighted part is in degrees right now. Again, as we said a while ago, it should always be in radians. So if you click radians in there, then it would already give us the sine function in this case. And we can see in here what we call the maximum, the minimum, and the period in this case. So let's try to label those parts in here first. So in trying to graph this sine function in here, we have this point as our maximum point, which is typically at 1. In this case, the minimum is in this point, which is at -1. Now, we have what we call our um, amplitude. So to get our amplitude in here, that will be the distance from the center to the either maximum or minimum. So again, that's what we call our amplitude. The next one, those are there. So this is a 0, and a 0, meaning the x-intercepts. The last one would be our what we call period. So to get the period here, we can see that period is the length of one complete curve. So when you say one complete curve, that'll be from here to there, then that'll be what we call a period. Let's see now what the length of one period is. As we may see in here, since this is in radians, then we have to see that everything in here is in terms of pi, which means this is at 0. This is basically at approximately 314, which is pi, and this is approximately 6.24, which is in fact 2 pi. So which means the length of one period in here is in fact 2 pi. But what about the amplitude? In this case, to see the amplitude from this point to that point, that vertical distance is typically 1 in this case. And in here, the amplitude is also 1. So the amplitude will always be an absolute value. It cannot be a negative value in there. Those are our typical parts of our sinusoidal function. Again, the maximum, the minimum, the amplitude, and the period. Let us now summarize what our analysis for a sine graph actually is, or sine function graph actually is. So that is in the form plus or minus sine b a sine bx. If it's a positive, therefore it starts at the origin, goes up, goes down, and goes back to its 0 again at 2 pi. If it's a negative, then it's going to consider an x-axis reflection where it will go from 0 going down to its minimum up to its maximum and go back to its 0 in there as one complete cycle. The amplitude A in here is the number before the sine. The absolute value of that one will be our amplitude. But if you want to compute for the amplitude, that will be maximum value minus minimum value for both the y's divided by 2. Now, let's go to what we call our b value, the one that is multiplied to our x. Then we can use this triangle in here with 2 pi on top, the b in here as the coefficient of x, and the p in here on the right, which is actually what we call the period. Period is the length of one cycle a while ago for sine x, that is 2 pi. So that, which means that in here, if we want to compute for p, then that will be equivalent to 2 pi divided by the b, or what we call our coefficient of x. Now, if we want to get what we call a frequency, frequency is simply the reciprocal of period, and that will be usually frequency is in cycles per second, or what we call unit of hertz. Let's consider answering this first question in here. It says a Ferris wheel has a diameter of 80 feet. Riders enter the Ferris wheel at its lowest point, 5 feet above the ground, at time t equals 0 seconds. Now, one complete rotation is 65 seconds. The question now is, which function models a rider's vertical height in t seconds? So with this being said, we can see it as follows if we graph it. So at t equals 0, where it started is 5 feet above the ground. So that means so at t equals 0, it's 5 feet above the ground. So if this is the t, it's at 5 in here. That's the minimum value. And then it will go up and it will go down again, right? And what will be the maximum here? So if the minimum is 5 feet above the ground, then that will be, this is 5. And the diameter, that means if this is our Ferris wheel in here, since the diameter is in fact 80, then that means the maximum is at 85, because that's 80 plus 5 in here, then that will be 85 feet for the maximum. Now, in order to get the amplitude will be the maximum minus the minimum all over 2. Then that will be 85, that's the maximum point, minus the minimum point, which is 5 feet above the ground, that's minus 5 divided by 2. So that'll be 80 divided by 2, which is a 40 in here. Again, that'll be our amplitude. This only means that if the amplitude is 40, then that means our value for A is also 40 in there. Now it says also that the one complete rotation is 65 seconds. That means from the minimum up to the minimum in here, then that is equivalent to 65 seconds. And that is equivalent to our what we call period, or the time it takes for one complete cycle. Now, in order to get our b value, let's use our triangle in here with 2 pi on top, the p and the b at the bottom. So you notice that I interchange the p and the b values in here because I simply want to get the b value. Therefore, the b value in here, according to this triangle, will be 2 pi over p. That will be 2 pi over our period is 65. Then that will be my b value in there. So all of this considered or being considered, then my answer will be as follows. That means I'm gonna put it on our y equals, in this case that will be a cosine b of x. In this case it's a cosine function, not a sine function, but still a trigonometric function. Then that will be letter b in here, where my a in fact turned out to be 40, in this case negative 40, and my b turned out to be 2 pi over 65 in this case. Trying to verify in our calculator what a negative cosine looks like so that we can see that it's in fact same graph with our Ferris wheel problem in here. Let's put in negative cosine of x. Again, it's in radians in there, and press graph. And as we can see, that will be the case for our thing a while ago. So let's zoom it in by pressing zoom 2 and enter. And we can see that in fact, it is what we have a while ago. Now consider our second problem about electric current. So our power bill talks about electric energy, which electric current is a part of in there. Electric current is in fact the amount of charge per second that flows through a circuit or flows through our house in there to be used by our appliances or electrical appliances or gadgets. So an electric current alternates sinusoidally with a frequency of 60 cycles per second. Cycles per second is in fact our hertz. At time t is equal to zero point 0.1 seconds, the current is at its maximum of 10 amperes. So amperes is the unit of current, which function describes I, the current, as a function of time t. So again, this is a sinusoidal frequency. So we can check it out as follows. It says at time t equals 0, then the current is at its maximum of 10 amperes. So that means the current in here, let's say this is 10 amperes or amps. And then after that, it's going to go down to its minimum. So if we can consider this in here, then we can see that at time equals 0, it's in here. Then it's going to go down to its minimum and go back up again, which means that at the minimum point, well, we should say that at the minimum point, that will be 0 ampere all in all. At the minimum, it will go back to 10 amperes once again after one cycle. So with this being said, we can compute for the amplitude and the period in here. So with this, we can say that our amplitude, or what we call the absolute value of A, is equivalent to maximum y value minus minimum y value all over 2. With that, we can see that this is the maximum value, which is 10, minus this is the minimum value, which is 0, and divided by 2. So that 10 minus 0 is 10 divided by 2. Then my amplitude is in fact 5 in there. Now, let's go get our period in this case. So it says here that the frequency is in fact 60 cycles per second. And once again, we said that the frequency and period are reciprocals of each other. Then that means we can say that the period is in fact 1 over 60. So that means from this point to that point, then the period in there is 1 over 60, meaning it took 1 over 60 of a second per cycle. Now to get our B, let's compute for that one. So we're going to use our triangle once again with 2 pi on top, and then P and B at the bottom in here. So to solve for the B value, which is the coefficient of x for either sine or cosine function, then B is equal to 2 pi over P. So that will be 2 pi over P, which is 1 over 60. And this will give me 120 pi for my B value. So with that, and so I can see this as follows. That will be equivalent to the following in here. Y is equal to A cosine B of x. Not considering the other numbers 0.1 and 5, we're simply considering the amplitude and period in here. So we can say that my A is in fact 5. In this case, this is a cosine, and my B is in fact 120 pi in that case. With that being said, then our answer will be letter A. Again, we did not consider 0.1 and 5 in here. So since they are the same for everything, we're simply considering the amplitude and amplitude for A and the period for getting the value of B. Let's verify our graph now using y is equal to cosine of x. In this case, I'm using my Desmos graphing. So I put y is equal to, I go to our keyboard app, go to cosine in that case, and put an x in there. So I would see now that, in fact, in here, this is what we call our cosine function, which matches our graph for electric current. So as we may see in here, this trigonometric function not only works for sine, it also works for our cosine function in that case. So for a cosine function, it looks like this for the cosine of x. And on the other side, it will look like this for the negative cosine of x. So once again, this is the graphic organizer for our sine and cosine trigonometric function with our a and b. Let me know if you have questions regarding trigonometric functions and its key features. And once again, tell me QUAN-do. You can do math.